Recording in progress. Okay, so this is our fourth video, which is the work and power in rotational motion. So here we have a merry-go-round. Okay, so in this example, we have a child applies a tangential force on this. So what will happen is that it will rotate. Okay, and the work dW, we have a work dW. So done by this force tangent while a point on there moves at distance ds. Okay, so while this we have the work while this one is moving at distance ds. Okay, so note that ds is just equal to r d theta. So our work is just equal to this f tangent. Okay, from the definition, work times the displacement. Okay, so here ds is equal to f tangential, okay, times we have r d theta. Okay. Now, so fr, this one is just the torque. Okay, torque around z. So we have here dw is equal to the torque z uh, d theta. Okay, so if you want to find the work, it's just equal to the integral from t1 to t from theta 1 to theta 2 uh, torque z d theta. Okay, so here uh, work done by a torque. This is we call this one is the work done by a torque, and for a constant torque, we have the work of a constant torque is torque along z. Okay, theta 2 minus theta 1. Okay, or we have the torque z times theta. Okay, so this is the work done by a torque. And this one is if the work done by a constant torque. So the work done is equal to torque times theta 1 minus theta 2. Okay. How about the work total? You can also uh, equate the work total. Okay. It's just equal to so for example, uh, we have actually the torque z d theta. Okay. Uh, where we can actually equate this one as uh, from the definition the I alpha z d theta, which is equal to I d omega z over dt. Okay, d theta, so this is the angular acceleration derivative of the angular velocity. So this is actually equal to uh, I d theta over dt d omega z. So we have actually I omega z, okay, d omega z, okay. So here, the work total, we can integrate this one, integral from omega angular 1, angular velocity 2, okay, I omega z d omega z. So this is equal to, so we can actually, this is actually equal to the work total. This is analog to the work and energy theorem, which is 1/2. So I omega 2 squared minus 1/2 I omega 1 squared. Okay, so that is the work total for what we call force you applied in this kind of situation. So also for power, so we have d work over dt. Okay, so this is the definition of power. We have the torque is theta d theta over dt. Okay, theta over dt. So we have actually the power, the torque, and we have the angular velocity. So angular velocity of the rigid body about the axis, torque with respect to the rigid body, so is equal to the power due to the torque. Okay, so that's the definition of the power due to the torque. Okay, let's have an example for this particular. An electric motor of constant 10 Newton torque of a grindstone, which has a moment of inertia of 2.0 kilograms per meter squared, about its shaft. So the system starts from rest to find the work done by the motor in 80 seconds and the grindstone kinetic energy K at this time. What is the power average is delivered to the motor? Okay, so let's find first, find the work done. So an electric exerts a constant torque. So we have a torque which is equal to 10.0 Newton meter. Okay, 10.0. This is zero point zero Newton meter. So what else do we have? We have I, which is equal to 2.0 kilograms meter squared. What's what else? We have also that this one, the torque Z is equal to I alpha Z, uh, where alpha Z na to, uh, alpha Z is just equal to, yeah, 5.0 radians per second squared. Okay. So another part exerts and another part about the shaft. The system starts to find the work. The bench against so average powers. The torque is only acting in this due to the motor when we start and then use this magnitude. Instant 8 seconds and its final velocity. So we'll choose this to calculate K. So this is from equation 9.11. So why is it that our angular acceleration is 5.0 radians per second? Okay. So third, and we have the moment of inertia. The system start from rest to find the work done. So which has a moment of inertia. So we're gonna use this motion with constant acceleration, angular acceleration. So let's go back to 10.7. How do we find the acceleration 10.7? Okay. So to get the 10.7, so we have the net torque is equal to I over alpha Z. So meaning alpha Z is equal to the net torque over the moment of inertia, which is 10.0 Newton meter over 2.0 kilograms per meter squared. So we have 5.0 radians per second squared. So that's why we have the angular acceleration. Okay, so next. Okay, so let's find first the change of our theta, which is from our constant acceleration, 1/2 alpha z t squared. So this is from constant angular acceleration. So we have 1/2 times 5.0 radians per second squared times 8.0 second squared is equal to 160 radians. Okay. So we also have our work which is equal to, so constant torque. So we have theta which is equal to uh, 10 point Newton meter. So 10.0 Newton meter. Okay, times 160 radians. So we have 1,600 joules. Okay. So find the work done by the motor in 8.0 seconds and the grindstone kinetic energy. Okay, so to find the kinetic energy, okay, from our motion with constant angular acceleration also, uh, we have that the omega z is equal to alpha z times t. Okay, so we have, this is actually equal to 5.0 radians per second squared times 8.0 seconds. So we have 40 radians per second. Okay. So our kinetic energy is just equal to 1/2 times the moment of inertia omega z squared. So we have actually, if you compute this one, 1/2 times 2.0 kilograms per meter squared, okay, times 40 radians per second squared. So this is equal to 1,600 joules. Okay. For the power, okay, the average power. So power average is just equal to joules per second. Okay, 1,600 joules per 8.0 seconds. So we have 200 watt or joules per second. So this is how to answer this one. So this is the end of our fourth video. So we're gonna continue to the next video. So please click like and subscribe for more videos like this.